Welcome to GATE Coaching. I'm S.A.ENGINEERING, Assistant Professor, Department of Mathematics. We are going to discuss about the quadratic form, rank, nullity. In the quadratic form, we come across matrix representation, canonical form, rank, nullity, positive definite, negative definite, indefinite. Quadratic form, a homogeneous polynomial of degree 2 in any number of variables is known as quadratic form. We have to note that it should be of degree 2. Some of the examples are given here. The first example is in terms of two variables x and y. 2x square plus 4xy plus 3y square is a quadratic form in two variables x and y. The second example is in terms of three variables x, y, z. X square minus 4y square plus 2xy plus 6z square minus 4xz plus 6yz is a quadratic form in three variables x, y and z. Next, the general quadratic form. The general quadratic form is represented as summation I equal to 1 to n, summation j equal to 1 to n, aij, xi, xj, where x1, x2, etc. to xn is defined as n variables and aij's are constant. If aij's are real, quadratic form is known as real quadratic form. Next, we can discuss about the nature, rank, nullity, index, signature of the quadratic form. Let x transpose ax be the given quadratic form, then it is said to be a positive definite if all the eigenvalues of A are positive. And next, if one of the eigenvalue is 0 and the other eigenvalues are positive, then we call such as positive semi-definite. That is, positive semi-definite if all at least one of the eigenvalues is 0. For an example, if we take a 3 cross 3 matrix, we will get 3 eigenvalues. If all eigenvalues are positive, we call that as a positive definite. If at least one is 0 and the remaining are positive, we call it as a positive semi-definite. If all the eigenvalues are negative, we call it as a negative definite. Negative definite, that is, if all the eigenvalues are negative. If one of the eigenvalues are 0 and the remaining eigenvalues are negative, then we call it as a negative semi-definite. If the eigenvalues are positive and some of the eigenvalues are negative, we call it as a indefinite. Next, we can discuss about rank, nullity. Rank, the number of non-zero terms in the canonical form of a quadratic function is called the rank of the quadratic form, and it is denoted by R of A, where A is a 3 cross 3 matrix. Nullity, it is defined as the difference between the order of the matrix n of A and the rank of the matrix R of A. It is denoted by capital N of A. The nullity n of A is equal to small n of A minus R of A. Next, we can see about the index. Index is the number of terms in the canonical form. It is denoted by P. Signature is the difference between positive and negative terms in the canonical form is called the signature of the quadratic form, and it is denoted by S. Therefore, the signature S is equal to P minus of R minus P, that is equal to 2P minus R, where P is index, R is rank. We can see one example. Reduce Q equal to 3x1 square plus 5x2 square plus 3x3 square minus 2x1 x2 minus 2x2 x3 plus 2x1 x3 into a canonical form by an orthogonal reduction, and find the rank, nullity, signature, index and the nature of the quadratic form. This Q we can define as X transpose AX. If A is a column matrix and X transpose is nothing but our row matrix. And A is nothing but, here we are taken a 3 cross 3 matrix. The entries are A11, A12, A13, and the second row A21, A22, A23, and the third row A31, A32, A33. And after that we will find the eigenvalues by determinant of A minus lambda I equal to 0. And next we will find the eigenvectors A minus lambda I into X equal to 0. Next we will check for the orthogonality. X1 transpose of X2 should be equal to 0 and X2 transpose of X3 equal to 0, X3 transpose of X1 equal to 0. Next we go for the normalized eigenvector D equal to P transpose AP, and next we will find the canonical form Y transpose dy, that is equal to, if we taken the Y as a column matrix and Y transpose is the row matrix, and we will write the D as the diagonal matrix. So we will get this form lambda 1 Y1 square plus lambda 2 Y2 square plus lambda 3 Y3 square. We will define the A matrix as A equal to coefficient of x1 square, half of the coefficient of x1, x2, half of the coefficient of x1, x3, and it's a symmetric matrix, that is 1 by 2 into second row is a 1 by 2 into coefficient of x2, x1, coefficient of x2 square, 1 by 2 into coefficient of x2, x3, 1 by 2 into coefficient of x3, x1, 1 half of the coefficient of x3, x2, and coefficient of x3, x square. The given quadratic form is 3x1 square plus 5x2 square plus 3x3 square minus 2x1 x2 minus 2x2 x3 and plus 2x1 x3. Therefore, the coefficient of x1 square is 3 and the coefficient of x2 square is 5. The coefficient of x3 square is 3. Remaining is half of the remaining. 1 by 2 into coefficient of x1, x2 is minus 2 and 1 by 2 into coefficient of x1, x3. x1, x3 is plus 2. This is 1 by 2 into 2. So it's a symmetric matrix. Therefore, this is 1 by 2 into minus 2 and 1 by 2 into this 1 by 2 into 2 and 1 by 2 into minus 2. Therefore, we will get A equal to 3 minus 1, 1 minus 1, 5 minus 1, 1 minus 1, 3. In the quadratic form, Q is defined as Q equal to X transpose AX. And the X is defined as a column matrix x1, x2, x3, and X transpose as the row matrix x1, x2, x3. And we find out the value of the matrix A, that is 3 minus 1, 1 minus 1, 5 minus 1, 1 minus 1, 3. The characteristic equation is determinant of A minus lambda I equal to 0. We know the value of the of A, and I stands for identity matrix. Here we are taken a 3 cross 3 matrix. Therefore, the identity matrix for the 3 cross 3 is 1 0 0 0 1 0 0 0 1. So that is determinant of 3 minus lambda minus 1, 1 minus 1, 5 minus lambda minus 1, 1 minus 1, 3 minus lambda equal to 0. We can solve the determinant. The first one is 3 minus lambda, 5 minus lambda into 3 minus lambda minus 1 into minus 1 minus of this minus 1 into 3 minus lambda minus 1 into minus 1, and the last one is plus 1 into minus 1 into minus 1 minus of 5 minus lambda. If we solve this one, we will get it as lambda cube minus 11 lambda square plus 36 lambda minus 36 equal to 0. If we factorize, we will get the roots as lambda minus 2, lambda minus 3, lambda minus 6 equal to 0. Therefore, the values of lambda are 2, 3, 6. Next, we can check the eigenvector. To find the eigenvector, we can define let x equal to x1, x2, x3 be an eigenvector corresponding to the eigenvalue lambda. A minus lambda I, x equal to 0. We already know the matrix of A. Lambda and A minus lambda I is 3 minus lambda minus 1, 1 minus 1, 5 minus lambda minus 1, 1 minus 1, 3 minus lambda into this column matrix x1, x2, x3 equal to 0, 0, 0. We can take the first eigenvalue when lambda equal to 2. Substitute lambda equal to 2 in this case. So if you substitute here, we will get it of 1, minus 1, 1, minus 1, 3, minus 1, 1, minus 1, 1 into x1, x2, x3 that is equal to 0, 0, 0. We have to note this here, the R1 matrix row 1 and row 3 are same. So we have to choose any one from that one. So we can decide R1 and R2. So x1 equal to 1 minus 3. Minus 1 into minus 1 is 1. Minus of 3 into 1 is this one. And next for x2, x2 equal to minus 1 into plus 1 is minus 1. Minus of minus 1 into 1 is minus 1. And next for x3, this is 3 into 1 is 3 minus minus 1 into minus 1 is plus 1. So we will get x1 divided by minus 2 that is equal to x2 by 0 that is equal to x3 by 2. All these are multiples of 2, therefore we will get it of x1 equal to minus 1, 0, 1. Second, we can take the value of lambda equal to 3. A minus lambda 2I into x equal to 0, therefore 3 minus 3 is 0, minus 1, 1, minus 1, 2, minus 1, 1, minus 1, 0 into this x1, x2, x3 equal to 0, 0, 0. Here all the rows are different, so we can choose any two of it. We will get the second eigenvector x2 equal to 1, 1, 1. And the last eigenvalue is lambda equal to 6. Substitute lambda equal to 6. Therefore, we will get it of 3 minus 6 is minus 3 and the remaining values are minus 1, 1, minus 1, minus 1, minus 1, 1, minus 1, minus 3 into x1, x2, x3 equal to 0, 0, 0. Here all the rows are different, so we can choose any two of it. We will get this x3. So we are taken 1 and 2. So x1 divided by 2, x2 divided by minus 4, x3 divided by 2. x3 equal to, therefore the third eigenvector x3 equal to 1, minus 2, 1. Next we have to check for the orthogonality. x1 transpose of x2 should be equal to 0. Let us check for the orthogonality. We know that the eigenvector for x1 is minus 1, 0, 1. Here we are taken x1 transpose. So my row wise we have to write in a row wise minus 1, 0, 1 and x2 is 1, 1, 1. So minus 1 into 1 is minus 1 plus 0 into 1 is 0 plus 1 into 1 is 1. So minus 1 plus 1 is equal to 0. And for the second, x2 transpose of x3 equal to, so we know that x2 second eigenvector is 1, 1, 1. So we have taken the x2 transpose, so we were written in terms of row 1, 1, 1. And the x3 eigenvector is 1, minus 2, plus 1. Therefore, 1 into 1 is 1. 1 plus 1 into minus 2 is minus 2 plus 1 into 1 is 1. So plus 2 minus 2, this is equal to 0. Similarly, x2 transpose, x3 transpose of x1, this is equal to 0. Next we find the length of the vector. Capital X1 equal to square root of, we know the eigenvectors as minus 1, 0, 1. So minus 1 the whole square plus 0 square plus 1 square, that is equal to root 2. And the length of the vector x2 equal to square root of, we know the eigenvectors of x2 equal to 1, 1, 1. Therefore 1 square plus 1 square plus 1 square, that is equal to root 3. Next, the length of the vector x3 equal to square root of 1 square plus minus 2 square plus 1 square, that is equal to square root of 6. So for the first we got root 2, for the second we got root 3, and for the third we got root 6. We can write the normalized eigenvectors as x1 equal to, we know the eigenvectors of x1 equal to minus 1, 0, 1. So the normalized eigenvectors are minus 1 divided by square root of 2, 0 divided by square root of 2 is 0, 1 divided by square root of 2. And x2, we got the length of the vector as root 3, therefore x2 equal to 1 by root 3, 1 by root 3, 1 by root 3. And we got the length of the vector for x3 equal to root 6, therefore the eigenvectors of x3 are 1, minus 2, 1, therefore x3 equal to 1 divided by root 6, minus 2 divided by root 6, 1 divided by root 6. So we can form a matrix. Let us define this as capital P. Capital P equal to minus 1 by root 2, 0, 1 by root 2. And the second means 1 by root 3, 1 by root 3, this is 1 by root 3. And for the third, 1 by root 6, minus 2 by root 6, 1 by root 6. So we have formed the P matrix. Next we have to check for the diagonalized. D equal to PA P transpose. We find out the matrix for P. We know the matrix of A and we know the P transpose. P transpose is nothing but interchanging the rows into column and columns into rows of P matrix. Therefore D equal to, this is nothing but P matrix minus 1 square root of 2, 1 by root 3, 1 by root 6. First row 0, 1 by root 3, minus 2 by root 6, 1 by root 2, 1 by root 3, 1 by root 6. This P transpose is nothing but interchanging the rows into columns. So minus 1 by root 2, 0, 1 by root 2. And next one is 0, 1 by root 3, 1 by root 3, 1 by root 3. And the third one is 1 by root 6, minus 2 by root 6, 1 by root 6. We already defined the A matrix in the beginning itself. It's 3, minus 1, 1, minus 1, 5, minus 1, 1, minus 1, 3. If you solve this matrix, we will get capital D equal to 2, 0, 0, 0, 3, 0, 0, 0, 6, which is nothing but a diagonal matrix. This 2, 3, 6 is nothing but our eigenvalues. Next we can write the canonical form. Canonical form is defined as the row matrix of y1, y2, y3 and the diagonal matrix 2, 0, 0, 0, 3, 0, 0, 0, 6 and the column is y1, y2, y3. We will get 2y1 square plus 3y2 square plus 6y3 square. By this we can define the rank, nullity, index, signature. Rank equal to number of non-zero terms in canonical form. So number of non-zero terms in canonical form we got 2, 3, 6. So all the 3 are positive, therefore this is equal to 3. Next, nullity. Nullity equal to order of the matrix minus rank of the matrix. Order of the matrix is a 3 cross 3 matrix. So 3, rank of the matrix is 3. So 3 minus 3 equal to 0. Therefore nullity here is 0. Next one, index. Index we defined it as P, that is equal to number of positive terms in canonical form. So we got the terms as 2, 3, 6. So all the 3 are positive terms. So this is equal to 3. Next one is signature. Signature is nothing but the difference between the number of positive and negative terms in canonical form. We got all the positive terms, so there is no negative term. So that is equal to 3 minus of 0, that is equal to 3. So it is a positive definite. This is one of the example. And next, the most important is get problems. Write the quadratic form of 2x square plus y square plus 3z square plus 2yz plus 3zx. They want the matrix of A. We know that the A can be defined as coefficient of x square and half of the coefficient of xy. Why we are defining like this? Because the variable present are x and y. So 1 by 2 into coefficient of xy, 1 by 2 into coefficient of xz, and 1 by 2 into coefficient of yx, coefficient of y square, 1 by 2 into coefficient of yz, and 1 by 2 into coefficient of zx because it's a symmetric, 1 by 2 into coefficient of zy, coefficient of z square. The coefficient of x square is 2 and the coefficient of y is 1 and the coefficient of z square is 3. This is off of this one is coefficient of xy is not present here. So this value is 0. So here also 0. And next one is 1 by 2 into coefficient of xy, y 1 by 2 into coefficient of xz, xz value is 3. So 3 by 2, here 3 by 2 and remaining is, this is 1. Off into zy's value is 2. So 1 by 2 into this is 1. So this is the matrix we got. This is the matrix A equal to 2 0, 3 by 2, 0, 1, 1, 3 by 2, 1, 3. This is the way of finding the matrix from the quadratic form. This is one of the gate problem. And next, reduce the quadratic to canonical form and hence find the nature of the quadratic form, rank, nullity, nature, canonical form, index, signature for this given expression. 10x square plus 2y square plus 5z square minus 4xy minus 10xz plus 6yz. This is given and we know how to define the A matrix. The matrix of the quadratic form is, we know that just now we saw the formula, A equal to, how to define the A matrix, capital A equal to coefficient of x square and here coefficient of y square and here coefficient of z square. The given variables are x, y, z. So we are defining like that and here off into coefficient of xy. So off into coefficient of xy means here 1 by 2 into minus 4. So here is minus 2. So minus 2, here also minus 2. And next one is off into coefficient of xz. Here a coefficient of xz is minus 10. So 1 by 2 into minus 10 is minus 5. So minus 5. And the last one is 1 by 2 into coefficient of yz, that is 6. 1 by 2 into 6 is 3. So the same 3. Therefore the matrix A is 10, minus 2, minus 5, minus 2, 2, 3, minus 5, 3, 5. Next we can find the characteristic equation, determinant of A minus lambda I equal to 0. So determinant of this 10 minus lambda minus 2 minus 5 minus 2, 2 minus lambda 3 minus 5 3, 5 minus lambda equal to 0. Here I is the identity matrix. We already said it's a 3 for the 3 cross 3 matrix. The identity matrix is 1 0 0 0 1 0 0 0 1. So we can factorize now. So 10 minus lambda into 2 minus lambda, 5 minus lambda, minus 3 into 3 is 9. Next one is minus of this minus 2. Minus of this minus 2 is plus 2 and minus 2 into 5 minus lambda, minus into minus plus, 5 into 3 is this one. And the last one is minus 5 into minus 2 into 3 is minus 6 plus 5 into 2 minus lambda. This is equal to 0. If we solve this one, we can get the lambda value as 0, 3, 14. We have to note that here one of the eigenvalue is 0. Therefore, the eigenvalues are lambda equal to 0, 3, 14. The rank, we know that rank equal to number of non-zero eigenvalues. Here that is equal to 2 because one of the eigenvalue is 0. Here 3 and 14 is a positive value. Therefore rank equal to 2. And next one is nullity. We know that nullity equal to order of the matrix minus rank of the matrix. Capital N of A equal to, it is defined as N of A equal to small n of A minus R of A. That is equal to, here the order of the matrix is a 3 cross 3 matrix. Therefore, this is equal to 3 minus the rank of this one is 2. Therefore, 3 minus 2 equal to 1. Next, nature. Here one of the term is 0 and the remaining terms are positive. Therefore, it is a positive semi-definite. Next one, we already discussed the eigenvalues will be the canonical form. Therefore, the canonical form equal to 0 into y1 square plus 3 into y2 square plus 14 into y3 square. Next, we can discuss about the index. Index equal to number of positive eigenvalue terms in the CF. The CF is, there are only two positive eigenvalues, that is 3 and 14. Therefore, this is equal to 2. Signature, difference between positive and negative terms in the CF. Here no negative terms, 3 and 4 is a positive term, so that is equal to 2 minus 0, that is equal to 2. Next one, find the rank of the matrix. The given matrix is 1, 1, 1, 1, minus 1, 0, and the third row is 1, 1, 1. The options are given here. Option A is 0, option B is 1, option C is 2, and option D is 3. Let us define this matrix as A. Let capital A equal to 1, 1, 1, 1, minus 1, 0, 1, 1, 1. Next, we have to find the determinant of this one. Determinant of A equal to 1 into minus 1 minus 0 minus 1 into 1 minus 0 plus 1 into 1 minus of this value. Therefore, we will get minus 1 plus 2. So, this is equal to 0. Therefore, the determinant of 3 cross 3 matrix is equal to 0. Therefore, there is no possibility of the rank is 3. The rank of the matrix is not equal to n. N is nothing but the size of the matrix. Size of the matrix is a 3 cross 3 matrix. Next, we can check for the 2 cross 2 matrix. Let us take the 2 cross 2 matrix. I am taken 1, 1, 1, minus 1. That is equal to 1 into minus 1 is minus 1, and minus of 1 into 1 is 1. Therefore, we are getting minus 2, which is not equal to 0. Therefore, the determinant of 2 cross 2 matrix is not equal to 0. Therefore, the rank of A is 2. Therefore, the option is C equal to 2. Next one. The rank of the matrix A is 5. So, they are given that R of A is equal to 5 and nullity of the matrix is 3. Then the order of the matrix, we have to find the order of the matrix. Some options are given here. A equal to 3, B equal to 8, C equal to 5 and D equal to 4. We can write the given R of A. Rank of the matrix A equal to 5. And nullity of the matrix, nullity we defined as capital N. So, N of A equal to 3. And we want the order of the matrix, that is small n of A. We know that capital N of A equal to small n of A minus R of A. So, n of A is 3, 3 equal to n of A minus 5. Therefore, n of A equal to 8. So, the option is B. And next one, the nullity of this matrix is equal to 1. They given the nullity of the matrix is equal to 1. They want the value of K. The options are A equal to minus 1, B equal to 0, and the option C is 2, option D is minus 2. So, they given the nullity of the matrix is equal to 1. Therefore, n of A equal to 1. We know that n of A equal to small n of A minus R of A. That is the difference between the order of the matrix minus rank of the matrix. We know the nullity is given here, that is equal to 1 equal to, it's a 3 cross 3 matrix. So, this is 3 minus R of A. From this, the rank of the matrix A equal to 2. And next, we want to find the value of K. So, the determinant K 1, 2, 1, minus 1, minus 2, 1, 1, 4 equal to 0. We can solve the determinant. So, K into minus 4 plus 2 and next minus 1 into, this is 4 minus of minus 2 plus 2 2 into 1 minus of minus 1 equal to 0. So we get minus 2k minus 2 equal to 0. Therefore, the k value is equal to minus 1. Our option is A equal to minus 1. Like this, we can solve many problems, many gate questions. We can continue in the next session. Thank you.